So as Jamie said, today I'm going to be talking about causation and the conservation of energy in general relativity. Yeah, so let's start. And this is joint work with James Reed and Andres Paez. A very, very, very early version of this started when I was an undergrad in my last year, like 10 years ago or something like that. But I stopped working on that and then recently came to the work again with James while I was at Oxford. Okay, so as you all know, the connection between energy and energy conservation and general relativity is a very long and complicated one. And the connection between causation and physical theory is also a very long and complicated story. You have, for example, Bertrand Russell thinking that you don't really need a notion of causation in physics. And you have many attempts to define or to come up with a good notion or a good definition of causation that is able to make sense of physical theories. So another very complicated and long story. And in this talk, I am going to kind of work on an intersection between these two long and complicated stories. In particular, I will consider the question of to what extent physical connection theories of causation are compatible with general relativity. And the upshot or the main goal is to challenge the most common position on the topic, according to which physical connection theories fail in the context of general relativity. That's kind of if there is a standard view about this question or this topic, I would say this is the standard view, which is general relativity and physical connection theories don't like each other, basically. So this is the agenda for the talk. First, I'm going to give a very, very quick introduction to physical connection theories of causation. Then I'm going to present the main challenge against the idea of using, or against physical connection theories coming from GR. And then I'm going to consider two solutions or two answers to the challenge. One that we call approximate symmetries, the other one we call asymptotic symmetries. And then I'm going to consider some problems. By the way, for reasons of time, I'm not discussing, and I'm going to come to this a bit later, but I'm not discussing a third solution, which has to do with pseudo-tensors. But again, I'm going to mention this later, and I'm more than happy to talk about this during the Q&A. So first, physical connection theories. Roughly, the idea of a physical connection theory is that when there are two events, A and B, say, and if there is a causal relationship holding between these two events, then according to physical connection theory, there should be certain link, certain physical process connecting the two events. For example, my kicking the ball caused it to move. So here, the idea is that there should be a physical process connecting the first event, Mike kicking the ball, or the feet hitting the ball, or something like that, and then the ball moving. So it could be like, for example, a physical process having to do with interaction. It will be a physical process having to do with the interaction between the shoe and the ball. And so the ball moves after Mike hits it. Now, this seems like a very, in a way, intuitive notion of causation. But I just want to remark that it's not the main one that philosophers like. The more standard one or the most common one is counterfactual theories or some variation of counterfactual theories of causation.
Sebastián, I have a quick question. Is there a reason why you're using physical connection theories rather than just theories of causation?
Well, this is the name that they have given to this particular kind of physical connection of causation. So there are some that are about physical processes, like the one I just mentioned, but there are others that don't say anything about a physical process connecting A and B. For example, counterfactual theories. There, you would only say that had Mike not hit the ball wouldn't have moved. But you don't have to give details about a particular interaction between Mike hitting the ball and the ball. So yeah, physical connection is just one case of a theory of causation. And there is a problem with physical connection theories, which has to do with absences. So famously, as this is a famous problem, like You might want to say that the absence of water or the lack of water, sorry, killed the plants. Or you might want to say that the lack of oxygen killed an astronaut in outer space, like a tragic death. But you get into trouble trying to say what the physical process is, because in one case you have an absence, lack of oxygen, and so on. But I'm not gonna go into that. I'm just showing you that there are other problems with physical connection theories of causation. Let's see. Okay, the most developed theory is given by Phil Dawes, who was a student of Wesley Salmon, who had his own theory, of his own physical connection theory. But here I'm going to be talking about Dawes' theory in particular, which is called the conserved quantity theory of causation. And it is called like that because for him, you have to, the physical process in question in some way has to do with conserved quantities. So to be more precise, there are two conditions in his theory. One is that a causal process is a word line of an object that possesses a conserved quantity, condition one. So that he uses to distinguish what he calls causal processes from other processes, like, for example, a shadow moving or a spot of light moving in the wall, which he thinks is not a causal process. And then a causal interaction is an intersection of word lines of causal processes, and they have to exchange a conserved quantity. What quantity? Well, it depends on the theory, it depends on the case, it could be energy, it could be momentum. Usually it's those two, but doesn't have to be. As long as it's a conserved quantity and it's exchanged during the interaction, that would count as a causal interaction according to this theory. There are more definitions here that I don't think, I'm gonna just put them for reference, but we don't really need to go into the details, and we can go back in the Q&A. Again, the intuition is simply that when you have a causal interaction between two events, there must be a physical process connecting the two events. And in that process, there has to be an exchange of certain quantities that are governed or described by conservation laws. Okay, the main challenge against physical connection theories in GR goes as follows in a nutshell. So in GR, conserved quantity is required, and I put star because we will come back to this, but normally people say conserved quantities require the presence of killing fields, right? Here, so here, for example, is the mass, and K there is a killing field. You can define the mass, the total mass, by using that kind of integration there, again, using killing fields. That's just an example. Then our space-time, the argument goes, lacks exact killing fields. So you cannot define integral conservation laws for our spacetime. And in particular, then you don't have conserved quantities in our spacetime. Conserved quantities in the sense of integral conserved quantities. And then, therefore, because if you don't have conserved quantities, you don't have causal processes. And if you don't have, according to CQTC, and if you don't have causal processes, then you don't have causal interactions. So there is no causation or causal interactions in our spacetime. Now, that kind of argument has been presented in the literature a couple of times. The first instance that I know of comes from Alexander Ruger in a paper called Local Theories of Causation and the A Posteriori Identification of this Causal Relation, 1998. But more famously, Eric Curiel in this 2000 paper, and I see Eric in the audience, he has this quote where he engages, in this paper, he engages deeply with the question about the compatibility of GR and CQ2C. And I want to read this quote because it's important. The spacetimes in which killing fields occur, however, are highly spatial and unphysical. Such spacetimes are unstable against arbitrary small inhomogeneities. The smallest speck of dust, the tiniest bit of out of place in only one spot in the entire spacetime, precludes the existence of a killing field. It is only in such unphysically dainty spacetimes, by dint of the daintiness itself, that one can define a quantity that behaves enough like energy, even to be tempted to call it that. It goes without saying that the actual spacetime we inhabit possesses no killing fields. And a couple of years later, Vincent Lamb, in his paper Metaphysics of Causation and Physics of General Relativity, also engages with this question, also kind of follows the line of Eric here. and says that this is a main problem for physical connection theories, namely that you don't have killing fields in general, and therefore you don't have conserved quantities, and therefore you don't have causation. Okay, now, I think it's important to be very explicit in what exactly the criticism is. I mean, intuitively it makes sense, but it's helpful to be very explicit so it is easier to see how to respond to it, right? So I'm going to present the same, or I guess a more precise version of the challenge or of the argument. We start with a premise like the following. There are two kinds of conserved quantities. Quantities that admit of both global and local conservation laws, called them kind 1 quantities, and quantities that admit only of local conservation laws. And this is important because in GR, and all of the people in the literature knows this, and even, I mean, the people I mentioned before also recognize this. You could define local conservation laws. Now, there might be reasons for why you think those are not good laws, and we can go back to that later in the Q&A, but you could define local conservation laws, right? So you need to distinguish between the integral laws and the local laws. Now, second premise, if spacetime S lacks killing vector fields, then S admits only kind 2 quantities. That is, if we don't have killing vector fields, then the argument goes you only have local conservation laws and quantities that are described by these local conservation laws. Then you have to give an argument for why these kind of laws are pathological. And there is a lot of work on this having to do with, for example, the coordinate dependence of the pseudo-tensorial quantities that you would use to define certain of these laws. Again, there is unfortunately not enough time to talk about that here, but we are happy to discuss it in the Q&A. That's not the premise we are going to be discussing here. We are just going to take that for granted, at least for the sake of the argument. Now, premise 4, our spacetime lacks killing vector fields. Hence, there are no non-pathological conserved quantities in our spacetime. In other words, because we don't have killing vector fields in our spacetime, then given what we just said, you can only define local conservation laws. But those local conservation laws are pathological, right? Why? Well, it depends on who you ask. And I'm going to assume that for now, but happy to discuss that later. The point is, if you think they're pathological, and then you assume that CQTUC requires non-pathological conserved quantities, that seems plausible. Then you have the following. If CQTUC is true, then there cannot be causal interactions in our spacetime. Because if CQTUC is true, for there to be causal interactions, you need causal processes. And for you to have causal processes, you need processes that have certain non-pathological conserved quantities. But you just said that you don't have any of those in our spacetime because we don't have killing fields. So if CQT is true, then there are no causal interactions in our spacetime. That by itself doesn't show that CQ2 is false. It only shows that if you take or CQ2C seriously and what you just said before, it just follows that there are no causal interactions in our spacetime. But presumably you want to say it's false or there's a problem with CQ2C, right? Because it seems natural to say that there are causal interactions in our spacetime. And so you have a contradiction, and then, I mean, the idea is that you have to drop CQ2C. This is a formal version of the argument, and then the way we do it like that is because it's more clear how are we going to respond to it. Essentially, the upshot of the talk is to attack premise 4, this one. That is, we are going to attack the question or the idea that our spacetime lacks killing vector fields. Okay. There is another way of attacking this, which is through the local conservation laws, but no time for that. Okay. So there are two ways of responding to premise 4. One is through the concept or through the notion of approximate symmetries. And then the other one I will let you know soon. It has to do with asymptotic symmetries, but this one is the first one. We want to point out, though, that though already kind of said something against this challenge, he was responding to Roger here, sorry, I'm not sure how you pronounce his name, but Dow says, as I understand it, our spacetime does exhibit the right symmetry. Global conservation laws do hold in our universe as far as we know. I take it then that the conserved quantity theory is not refuted. Unfortunately, he didn't really say much. So what exactly he had in mind is a bit unclear. Also, we think that what he had in mind is something like, to a very good approximation, there are global conservation laws in our spacetime, or something like that, or at least that's our charitable reading, but he didn't say much more. Here is what we are gonna say, so even if he didn't mean this. So remember, premise 4 says our spacetime lacks Killing vector fields. Now, the thing is, we think that whether or not spacetime admits certain symmetries is a vague matter or it could be seen as a vague matter in the following sense. Whether spacetime admits symmetries could come in two flavors. It could admit them in an exact way, like perfectly if you want, but it could also admit them to a very good approximation. And then we think that in physics, and I will show an argument for that, the second suffices, and it should suffice for the purposes of CQ2C. That is for the purposes of applying conserved quantity theories of causation. Now, that's not enough though. Even if you say, okay, sure, maybe there is a sense in which spacetime has symmetries or Killing fields, is just that it has them in an approximate way. Even if you say that, you have to say more. You have to say that, I mean, if you want to defend the CQ2C theory, you have to say those approximate symmetries are enough in order to apply CQ2C. And that would mean that you should be able to derive certain conservation laws from those approximate symmetries. Because if you can't, then, well, what's the point of bringing them to rescue CQ2C? You have to be able to derive certain conserved quantities. Okay. So the notion of approximate symmetry actually has a long history in physics, going all the way back to and probably more, but as far as I know, to 1968. This paper by Richard Matzner called Almost Symmetric Spaces and Gravitational Radiation. The idea, and the way Matzner kind of introduces his idea about approximate symmetries is something like this. Look, normally, when you think about Killing fields, they have to satisfy, or they have to, their flow preserves the metric. Exactly, right? And you have the Killing equation, and that's kind of what it's supposed to capture. But what if you want to preserve the metric up to a certain order? Not exactly, but to a very good approximation. Then what? Can we do anything with that kind of idea? Can we develop this into a more rigorous formalism? And he thinks he can, and then he develops his own, I guess, program about approximate symmetries using that idea. Now, we're not going to talk about his original proposal, Matzner's, but we're going to talk about or mention a paper by Abraham Hardy from 2008, which has his own version of making sense of approximate symmetries and conservation laws. And again, this is more well known in the physics literature, but in the philosophy literature is very rarely discussed, the existence of these approximate symmetries in GR. There are some exceptions, actually one that is a very recent one by Brian Pitt. In that paper, there is a paragraph where he mentions approximate symmetries. He doesn't go into a lot of detail, but he does recognize actually Matzner's paper, and he cites other papers that go in this direction.
So, Sebastian, can I ask a quick technical question? The paper.
Yeah.
I think it's quick technical clarification. If not, tell me to hold off until the end. So the Hardy paper you refer to, he actually generalizes affine collineations, not Killing fields, and it's not clear. Are you going to discuss that?
Yeah. Thanks. I'm going to discuss that. Yes, but good, good point. So there is some. Let me talk about that, and then I can go back to your question. So let me that's going to come in like 2 slides, okay? So bear with me. Before that, let me consider kind of Hartree's paper, what he's doing there. And there is a terminology issue here, which is sometimes they call some of these general versions of symmetries, which are not really Killing fields, but as you say, generalized collineations. Sometimes people in the literature call this almost Killing fields because they behave like Killing fields in some sense, or because they are more general versions and they collapse to Killing fields in very specific circumstances, like in Minkowski space-time. Anyway, that's a terminology issue, but let me call them Jacobi fields, which is what Hardy, he shows these are Jacobi fields. Anyway, you consider a generalized version of Killing equation. In what sense generalized? I will come back to the next slide. Then you find a field that satisfies those generalized symmetries at a given space-time point P. And you require that that field that satisfies those generalized symmetries at that point, space-time point P, are recovered from the initial values. I mean, you have a well-posed initial value problem. You have an initial value and first derivative. You want to recover from those conditions. And then you say that fields satisfying these conditions become approximate symmetries near P. You started with P, and they satisfy those general notions of symmetries at P exactly, but then you move a little bit further away, and then the idea is that they should approximate in some sense the symmetries that were exactly satisfied at point P. And you can use these fields to construct conserved quantities. That's kind of conceptually what's going on. Now, for reasons of time, I'm gonna have to go very quickly over this, but in the Q&A we can come back to that. But this has to do with what Eric was asking, or pointing to. Like, you can think of like some sort of hierarchy like this one. Killing fields are defined by the equation above, right? Their flow preserve the metric, exactly. Then you can generalize that idea, or go to I guess more general, if you want, equation one, where you say that the field satisfies the metric up to a certain scaling factor. In that case, you have a conformant Killing field, or up to an exact constant, like for example, you fix C, in which case you have homothetic fields. The terminology is, I mean, the names don't really matter. The point is that each step you go down, you go to a kind of more general idea. So now you go and consider what's called affine collineations, which are given by the third level there. And the important thing is that they generate infinitesimal affine transformations, and they preserve the Leavitt-Civita connection. And then Hartree shows that the fields, every field that satisfies that third step satisfies this fourth step, which is the equation of geodesic deviation, also known as the Jacobi equation. However, there are fields that satisfy the Jacobi equation, fourth row, that are not affine collineations. So in a way, this is a more general, there is a sense in which this is a more general condition. Okay, so it's not really Killing fields, but you have cases where everything collapses into Killing fields, for example, in Minkowski space-time. Okay, so 4 important properties of almost Killing fields, but this is a terminology thing. You can call them Jacobi fields too. 4 important properties that Hartree emphasizes. These symmetries, I define them through a point and then expand it, but actually he does that, but then he also does the same for a word line. And he says, consider this is the word line of an observer, then kind of apply the same idea, but you kind of go out of the word line instead of out of the point. And you can do that. It's more complicated, and the details are in his paper, but if you do that, then you kind of do the exact same reasoning, and then you have some symmetries that are exact along the word line, but are approximate as you move a little bit further from the word line. That's what I said there in point 2. And they can be extended to finite regions. And the most important thing for our purposes is that you can use them to define conserved quantities. Integral conserved, you can find integral conservation laws. I wrote one there, and then if you replace that psi for example, a Killing field, you have the standard Komar momentum or something very close to it, but that psi there doesn't have to be a killing field. It could be a generalized collineation or and then you have a slightly different definition. Well, it's going to look different, but it's the same conceptually. Anyway, I'm running out of time, so I'm going to be a bit quick in the last part of the talk. So the proposal then is, okay, let's grant Harty that you can define integral conservation laws using his kind of program. Then what? Well, then the proposal is maybe you can use these kind of things to define, or that's enough for you to define conserved quantities. And actually, I forgot to say, he also defines almost conserved quantities. So some of these fields don't exactly give you a conservation law, but give you a conservation as semi-conservation law, something that varies so slowly under certain scales that it's almost as if it was conserved. Anyway, say we get that, then what? Well, we can then modify the original proposal by Dow a little bit and say, look, we don't need the conservation laws maybe in the standard way that always being defined. Maybe those conservation laws or almost conserved quantities that you can define via approximate symmetries are all you need in order to define causal processes and then causal interactions, and then run the program with those. Why you might like this or not might like this, well, we can talk about this in the Q&A, but it's a proposal based on an approach developed by Harty. And the important thing is to answer or to see if this solves the problem of distinguishing causal processes from non-causal processes. We think it does, but we can talk more about that in the Q&A. Very briefly, let me consider the other way of facing the problem, which is, or the challenge, which is using asymptotic symmetries. So it's well known that for asymptotically flat spacetime, we can define integral conservation laws generated by asymptotic symmetries like the ADM energy and the ADM linear momentum, right? Now, so what? Well, our spacetime is not asymptotically flat, so what do we do with this information? Oh, and there is, I don't know why, okay, they are not in order, but these are examples of the, I mean, this is the ADM energy and the ADM momentum. Well, here is where we talk a little bit about models. So imagine you have a very dense star surrounded by two planets, like the orange and the red one, right? And say you want to model the spacetime around the star, the yellow ball here in this diagram. Well, it's typical in physics that if the object, the system, is taken to be approximately isolated, right? If the influence of the other objects is negligible, then it's fine to model for the purposes of certain theoretical calculations or even experiments to model the system as if it was as if it was isolated, like properly isolated. And then you run the model and see what you get. And then you can introduce complications later. Now, typically, models of isolated subsystems in GR are asymptotically flat. The Schwarzschild solution is an example. And so, armed with this asymptotically flat model, we can define then integral conservation laws, as we just said, the ADM energy, the ADM momentum, and so on. And these properties can be described to the system as long as it is treated as embedded in an asymptotically flat spacetime, and then we can apply CQ2C to the case at hand. That's the hope, at least. The hope is, look, you start with a complicated situation. If the original system, or if there is a target system that is approximately isolated, you model it as if it was isolated. This is a very common strategy, not just in GR, but in physics in general. And then you derive certain properties from that model. And then the hope is those properties represent to a certain extent properties of the system, even if it is not completely isolated in reality. So the proposal is our universe is such that it has approximately isolated subsystems, and such subsystems exhibit approximate asymptotic symmetries in the sense that each can be adequately modeled, each system, each approximate isolated subsystem can be adequately modeled as if it were within a spacetime that is asymptotically flat. Okay, now, and this is the last thing, one of the main objections to this kind of proposal is that by Patrick Durr and others, but this is a famous quote by Patrick, in which he says that our universe is not asymptotically flat, so we shouldn't be realist about properties that we derive from models that assume asymptotic flatness. In a nutshell, that's the complaint. And our response is, sure, the universe is not asymptotically flat, but we can still make inference about subsystems in our universe using or assuming that certain systems are approximately isolated. So here, for example, in this diagram, if you assume that star is approximately isolated in the sense that the other objects for the purposes of your theoretical calculation or experiments don't really affect much what's going on in the region inside the ring, the red ring there, then you can treat that as if it was an isolated system and then derive properties for that using that model. And it suffices to derive certain properties. Now, another important thing is that in the model, asymptotically flat, you imagine mathematically you go to infinity, either space-like or time-like or whatever, right? But you don't have to take that literally. In the actual target system, you can say that what the model represents as happening infinitely far away can be taken to represent what's happening just in the boundary there, in that ring, if it's nearly flat. So that's another important point about how to not be very literal about models when modeling real target systems. Okay, so to wrap up this kind of response, even if one might object that the ADM energy only holds for asymptotically flat spacetime, it's still reasonable to believe that something very much like the ADM approximates a certain property of the target system if such a system is isolated. And also, skepticism about asymptotically flat models is dangerous. It's also actually could lead you to a self-undermining circle. If you are very skeptical of asymptotically flat models, then you have to be kind of skeptical about GR in the sense that these models have been used both to develop the theory, but also to a good extent to confirm gravitational waves or like the modeling of the Schwarzschild solution and things like that. If you think those are essential, then being very skeptical about what the asymptotically flat models represent has the risk of being a bit skeptical of GR. And to end, sorry, I lied before, this is now to end, there is a problem with this proposal thought, and we want to leave it there, which is, sure, okay, suppose you assume that ADM energy is something, is a property that to some extent correspond to certain systems that are approximately isolated. Then what? Notice that you don't really recover the picture you wanted with CQTC, which is a picture where you have causal processes interacting with one another and then exchanging something. Because ADM energy is a global property that you define for the whole space-time, not just for a localized object. And so you didn't quite recover the intuitive picture you wanted. You recover something like global conserved quantities of the whole thing. And then it's not so clear how you can then recover the classic story of things interacting with one another that is behind CQTC. And there are some things we can talk about related to explanations in general relativity. I think much more needs to be said about both models and explanations in the context of general relativity. And the door to pseudo tensors, I'm going to leave it there, but I'm not going to open it right now. We can open it in the Q&A. So thank you.
Thank you so much. Questions? Ramesh?
Yeah, so.
Can you hear that, by the way?
You hear me?
Yeah, I think so, yeah.
Okay, Eric can hear me. Good. So early in the talk, you said that locally conserved quantities are pathological. But then it seemed to me that later in the talk, you were in fact invoking locally conserved quantities in one form or the other. So could you elaborate on this? What is the pathology and how are you getting over it?
Good. So when I said, I mean, and this is my reconstruction of what I take the argument to be in the literature, for example, by Eric. They say sometimes that local conservation laws in GR are pathological, for example, because if you do it with pseudo tensors, as many people have been doing, right? Then, well, the problem is that there are no geometric objects, in the sense that once you change, for example, frames or coordinates, then you change the values of the whole thing, and that maybe you can even make it go to 0, right, by a change of coordinates. And then you might get worried that if this really is a quantity, a real physical quantity, maybe it shouldn't go to 0 just by me changing the coordinates. That's one of the many options. There is another criticism, which is, so that's one criticism, and that's against pseudo-tensorial laws. In the talk so far, I didn't talk about the pseudo-tensorial laws. When I talk about local laws, and this is a good clarification, thanks for asking, I meant like Harty's program. Yes, it's local in the sense you start in a point, or you start in a word line, and then you start expanding. But then you recover the integral laws, right? And so in that sense, you can just maybe in some sense skip the local part and go to the integral. Or if you want to talk about the local part, notice that he's not using pseudo tensors for defining these things. He's using these killing fields, or sorry, generalized collineations, but he's not using pseudo tensors. So to put it in like 10 seconds, when people say local quantities are pathological, they usually mean pseudo-tensorial laws for energy conservation or propagation of energy. And that's what I didn't discuss in the talk. Does that make sense?
Yeah, thank you.
Yeah.
Eric and then Jacob.
So thank you for that. I have it was a very I'm in a hotel room. Let me close the door. I just realized it's actually quite noisy outside. There, that's better. Sorry about that.
No.
Okay, so I have several comments and questions. I'll just ask one now, and Jamie can throw me on the back of the queue, and if there's time, I'll get to more. Well, although I do want to make one comment about this pathological business.
Mm-hmm.
So I can't speak for anyone else. I can't speak for anyone else, but at least for me, the distinction I was discussing in that old paper, and that I think is still an interesting and relevant distinction to keep track of, is the distinction between continuity equations that are formulated entirely using derivative operators and integral laws that are formulated using integrals, differential quantity over some finite region of space or space-time. And if I use the word pathological for a quantity that satisfies only the form but not the latter in that paper, then I deeply regret it. I certainly I don't think I did, but if I did, I was completely.
You didn't. No, you didn't.
It is true that I think pseudotensors, I'm not sure I would call them pathological. I just think they're meaningless. I guess it's a toss-up which one you think is worse, being pathological or being meaningless. But putting that aside, so yeah, I just want to clarify that at least so far as I'm concerned, local quantities in the sense that I just characterized as obeying a continuity equation formulated using only derivative operators, I think there's nothing wrong with them at all. They're very useful. They're wonderful, beautiful, great. But I don't think that. But I don't think that they suffice for the kind of causal theories that people like Dow want to put forward. So now, first question. God, I have so many. Where to start? Let me ask you about. Let me ask you about the physical role of. No, let me actually start at a very high level and kind of a more philosophical question. So Dow, at least, and Salmon also, they really wanted to give an account of causation that in some sense was fundamental, that should be considered as part of physical theory, that lives comfortably in fundamental theory. Other person, whose name I can't remember, I'm sorry, are talking about. It seems like you're more in the camp of talking about giving an account of causation that's not supposed to be physically fundamental, but is something that's supposed to be approximative, useful, maybe a psychological heuristic or something along those lines. Can you just clarify exactly what kind of account of causality you think you're trying to defend?
Good. Yeah, so Dow in that book in particular, like he says something like he wants to give a theory of causation that is empirically based, right? And he goes on and on about what that means. And one of the things he says at some point is like, it's a conception or notion of causation that comes from the physics. Now, the fundamental side of things, maybe Salmon has that idea. I am not sure. I mean, this is not that important, right? I mean, whether or not Dow meant the fundamental is not that important. What matters is what we are trying to do right with this project and how we are interpreting Dow. And let me put it this way. If we go through the fundamental route and say, look, we want a notion of causation that, in a sense, emerges only when you have exact conservation laws or something like that. Then I'm worried because you wouldn't even have that in classical mechanics, that you will always, like once you try to apply this notion of causation with a very strict or rigorous kind of very demanding notion of what is a genuine conservation law that has to be kind of satisfied exactly, then you might doubt that we don't even have that in any theory, right? We of course can write them. We can write exact conservation laws and integral conservation laws for classical mechanics, electromagnetism, and so on and so forth. But whether or not the world is exactly represented by those models and theories, we don't think so. I mean, there is always going to be some approximation. And so requiring too much from the very beginning, I think, might be like a hopeless task. I think it's, in other words, yes, maybe it's fundamental, but fundamental not understood as you take the exact solution of the physical theory and then try to derive causation from that. But fundamental in the sense that whatever the world really is, and is presumably not exactly described by the physical theories, then you can kind of extract causation from there through approximations. But this is me. I don't know if James has a different, I guess, perspective on this, but does that make sense? I mean, we just think that taking too literal the physical theory, the model itself, and demanding only the exact solution to count as fundamental might be like a too strict or too strong of a requirement for how physical theories represent stuff. So I don't know if that makes sense to you.
I have a few things to say, but they actually dovetail with further questions I have, so I'll just throw myself at the end of the queue and raise it next time around.
Thanks.
Okay, so Jacob and then Mike. Oh, your audio is all garbled. Do you want to write it in the chat and then I can read it out, or? Oh. Okay, Mike, how about you go ahead and then we'll go back to Jacob when he returns.
Sure. Thanks, Sebastian, for this. I guess I have two questions. The first one's pretty quick. If you could go back to the argument reconstruction with the full. So the high level philosophical question that hopefully is actually fairly quick. Mm-hmm. Is it really, bearing on the previous line of question from Eric, is it really that 8 holds as far as the conversation about CQTC is concerned? I'm reading our space-time here as a model of the theory, and if the sort of pragmatic kind of motivations that we're interested in an account of causation, or we're interested in having an account of causation for, it doesn't seem like it's referring to the same object anymore, because now it's outside of the taking too literally the theory we have. I guess another way of putting this is I worry that smuggled into this way of framing is a metaphysical conception of space-time, separate from our theory of general relativity, which happens to be a space-time theory whose models are spatiotemporal.
So let me actually ask you to clarify something. So are you saying that you're questioning C or number 8, or you're questioning what exactly in this you want to go into?
So if the intuition following the word causal interaction is causal in the sense that the conversation you want to have about CQTC is causal, then that exists in a conversation that isn't predicated over world models of a particular physical theory, namely GR. And so why would those causal interactions be in the object that is just a model of the physical theory?
I see. I think, let's see if this is, I think I see what you're saying, but let's see. So we have, I guess, the universe, right? The real stuff there, right? Outside. And presumably we want to say there are causal interactions there. Well, I guess for the sake of the argument, say there are causal interactions in the universe, like a binary star produces gravitational waves, and maybe that's a causal interaction of some sort, or a causal process of some sort. Now you use GR to represent that thing out there, like space-time and these objects living in space, right? And you want to say that there is a sense in which there are causal interactions. Yeah, I mean, the models in a way recover those causal interactions that you see, so to speak, in the outside world. So you have the world, then you assume there are causal interactions, you think there are, then you have GR as a model of certain systems outside, right, in the world, and then presumably GR, you might want it to have the resources to model those causal interactions. So for example, if you're a counterfactual person, you would be happy because you would say, look, if, I don't know, if there hadn't been a binary star here or something like that, then no waves would have been produced. Now, that you are talking about the model there, but obviously in a way you're talking about the real system. So it's like it gets complicated, but as long as you're careful about when you're switching from the system to the universe, it should go through. So I think the problem with CQ2 here is that not even once you go to the space of the models and you see what's going on, you do see counterfactual dependence between certain properties in the model. And so that's good because that seems to reflect some causation if you're a counterfactual person in the real world. But you don't have, or the argument goes, conserved quantities in the model or certain things in the model that allows you to model causation if you think causation is a matter of physical connection. Does that make sense? And presumably you wanted to be able to model causation. At least is one of the ways of reading this. Does that clarify?
Yeah, I think I'm still, I worry that when the conversation is dislocated from the original commitments to fundamentalists thinking about cause, that actually there's just a much easier route than all of this, which is to say general relativity is a theory like any other. We want it to help us do as much as it can. If it can't do this last bit, then we just say we don't help ourselves to the full apparatus of the theory in order to generate those causal claims. And that seems fine because general relativity is not a complete theory anyway. So I guess maybe that's where my concern lurks, that too much is lost in the move. For the sake of this conversation, or this debate, too much is lost in the move to pragmatism about CQTC. And I'll drop my other more technical question because that ended up being a longer conversation.
Okay. Do we want to go back to Jacob now then?
Can you hear me now?
Yeah.
Okay, great. Thank you. Sebastian, it was a great talk. Thank you so much. I'm sorry for the technical problems. Also, I'm sorry for being a little late to the talk, coming from another seminar that went over. So I apologize if you addressed this at the beginning. So I have two questions, both conceptual. Maybe they're somewhat naive questions. The first is, when I think about causation at the human scale, when I use cause and effect to pick out certain real world patterns that I notice in the world around me, I'm thinking about things like, does smoking cause cancer? If someone writes something down and then a century later someone reads it and it inspires them to write poetry, I'm thinking about cause and effect in those terms. But even beyond that, certainly we have, great empirically successful physics nowadays, but it's conceivable that, I don't know, telekinesis or some kind of, non-physical cause and effect, could exist. I mean, we don't think that it does, but if it did, we would certainly talk, I think, about cause and effect, about people mentally causing things to happen without the medium of particles or conserved quantities. So I guess my question for you is, why should I take this particular theory of causation as being the right one or the good one when it seems so disconnected, practically speaking, from the ways I use causation in the world around me, and may not even be comprehensive enough to account for all conceivable kinds of cause and effect? Connected to that, there are a lot of concepts that we like to use as human beings that make sense on human scales that we don't think are fundamental. This doesn't mean they don't exist. I mean, the color red, I would argue, exists. It may not be fundamental, but it exists the way that tables and chairs exist. So why should I even be looking for a fundamental definition of causation at all? Why shouldn't I be satisfied with causation picking out macroscopic patterns in the world around me, like temperature, which we don't think is fundamental, or pressure, that are nonetheless objective, we all agree on, are very useful, but don't seem to play a fundamental role in, say, the standard model Lagrangian?
Good. So yeah, thanks for your question. So at least two things. One is, notice we are not defending physical connection theories in general, or saying they are the best theories. We are just showing that we think there is much more to be said in their favor against the main challenge raised against them, right? So we're showing that there are other ways not explored yet by which physical connection theories or Tao could maybe try to respond to the challenge. Now, having said that, obviously we think physical connection theories are appealing. Otherwise, you might think why we are wasting our time trying to defend them, right? And I mean, part of the thing is, look, you might think that, so the telekinesis case, actually Jonathan Schaffer has a very early paper where he talks about magic cases, where he says like kind of the same thing, like you could make something in magic. If you take magic seriously, you presumably could change something far away from you and without any intermediation of physical processes and things like that. Anyway, and that was supposed to be a challenge to the physical connection theory. So physical connection theories have challenges. The other one is the absence, causation by absence, that I talked in the beginning of the talk. But the problem is that the rival also has big problems, like counterfactual theories have a lot of problems, particularly the overdetermination problems when you have multiple counterfactual dependencies all interacting at the same time. And then you have other problems that have to do with, it seems you have too much causation if you go all the route through counterfactual theories. You might think there is not a real fundamental theory of causation. That could also be the case. But physical connection theories are supposed to be inspired by physics. So it's a bit ironic that they are, I mean, physicists, the idea is usually have intuition that with something causes something else, there is certain interaction. Seems like a very basic intuition, like a physical process, hitting something, a field, hitting something, two fields interacting, something like that. So that seems to be a key intuition in physics, and maybe that's what you are trying to rescue and show, that in physics you actually have something like this playing around, this kind of notion. And then you get all these problems like the general relativity problems with conserved quantities, and you have the problem with quantum mechanics, presumably. And Tracy Luffer has a great paper where he goes on to different problems applied to fundamental physics of physical connection theories. So depends who you are. Within physical connection theories capture a lot of what's going on in physical models and physical theories. Whether or not it captures all is up to debate. But yeah, that was not our goal here, to defend it from all kinds of problems, but this particular problem. Oh, are you? Yeah, are you there? Okay.
Okay, well, we've got approximately 2 minutes before we have to start colloquium. So Eric, you have time for a quick question.
Okay, I'll try to be quick. No one in the room has a question since I've already asked one. Okay, so wow, I'll try and be brief. There are in an unpublished manuscript I have, I count at least 12 different notions of approximate symmetry in GR. About half have been talked about in the literature, half I just came up on my own because it's really not very hard to come up with ways to characterize the idea of an approximate symmetry. Over half of them do not have associated with them any notion of anything like an almost conserved quantity. Harty's notion I find very unphysical. I have no idea what it means physically. I have no idea how to apply it. For instance, if I'm modeling the interaction, if I'm modeling something as simple as the orbit of a planet around a central sun, I have no idea how to apply it, and I have no idea what the physical significance of the application is. So why are you guys focusing on this? What's the physical significance, and why are you not considering the 11 other possible candidates?
And if you can answer all of that in like 30 seconds, that would be great.
Well, I mean, actually,
that was me. I'm sorry.
If you don't mind sharing with us your manuscript, that would be great. I mean, we don't consider the other 11 because we don't know them, but also like Harty's thing. One of the things that is intuitive, I think, about Harty's idea is like you recover all of the things in the cases you expect them to recover. So in Minkowski spacetime, you get back the Killing symmetry. They degenerate into Killing fields, and then you get the typical conserved quantities. And then the planet, very quickly, the planet around the sun, that's something that we think is actually very hard to even give an intuitive explanation of what's going on causally, explicitly, analytically, right? I mean, is that
I agree. Yeah, I agree.
So we have even problems in that very basic case, but not just for DAO, but for anybody. Even forget about DAO. Everybody trying to explain very explicitly what's going on in the model and how do you see the things you see, because you don't have an analytic solution usually, right? So that's a good question, and I think it's a problem for everybody. Now, the Harty thing we can talk more about maybe over email or later.
Maybe you and James and I can get together and over Zoom and have a talk about it.
Yeah, that would be great.
You.
Yeah, thanks for the questions.
Well, thanks again to Sebastián.
Thanks. Enjoy colloquium.
Thanks. See you. Enjoy teaching.